Why, hello everybody. Today we're going to go on to section 14.3, which deals with arc length and curvature. So let's begin. First thing I want to talk about is arc length, and then we'll talk about curvature. If I have a curve, and I'm going to draw it as a two-dimensional because my paper is two-dimensional. If I have a curve, just like you did in Calc 2, if I have a curve and I want to figure out the arc length maybe from this point to this point, I have some parametric representation for that curve, and I actually want to figure out if I take a string and move it along, and just tape it to the curve all the way along, and then straighten it out and put it against a ruler, how long is it? That's what we want to do. And what we're going to do is we're going to break up this curve into a bunch of little pieces. And then what we're going to do is we're going to approximate the length of the curve using the line segment that connects each of the given points. That's what we're going to do. So first of all, I want to talk about if I want to approximate this line segment from this point to this point, how do I go about doing it? All right, now let's just go back and review. If you had a point here and a point here, and maybe this point's coordinates are x1, y1, z1, and this point's coordinates are x2, y2, z2, and I could do more than approximate. If I want to determine the distance between those 2 points, I'm just going to use the distance formula, right? And the distance between those 2 points is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Okay? And I'm going to call that the distance from here to here. We usually use the letter S for arc length. I don't know why. It'd be interesting to go back and see in history why they decided to use S for arc length. But this one little piece we can call delta S. So we will say delta S is approximately equal to this amount. Okay? Now I'm going to rewrite this just to make life a little bit easier for myself today. Notice we can rewrite x2 minus x1. That's how much my x coordinate changed as I moved from this point to that point, right? So I'm just going to write that as delta x squared. And the y2 minus y1 is how much y changed. And the z2 minus z1 is how much z changed. Okay, now those of you at home, you could have either printed out my lecture notes, but if you didn't print out my lecture notes, what I'm going to do in the next few minutes, I don't want you frantically there copying. I'll tell you when we get to the point where you want to copy the formula. But this distance from here to here, we can approximate by the square root of how much your x coordinate changed, plus how much your y coordinate changed, plus how much your z coordinate changed. All right, so right now, I want to approximate this distance, delta s, and this is what we just came up with. All right, now what I'm going to do for that delta s is all I'm going to do here is divide by delta t squared and then multiply by delta t squared, because I think most of you would agree that that's really just a form of 1, right? Because the delta t squareds really cancel. All right, then what I'm going to do is I'm going to change this to the square root of this piece times the square root of that piece. And I think all of you would agree the square root of delta t squared is just delta t. Delta t is no longer underneath the square root. All right, now I'm looking back at this curve, and I'm saying, you know what? This delta s is not exactly equal to the length. It's off by just a little bit. All right, like if you had a curve here and you approximate it with that line segment, you can see that you're off by a bit. But as you let the points get closer and closer and closer and closer together and add up more and more and more and more and more tiny little line segments, that approximation will get better and better and better for the curve. And as delta t goes to 0, the sum of all those little line segments will equal the length of your curve. So I'm saying, okay, well then, let's let delta t go to 0. Well, I think most of you remember from your Calc 1 days that as delta t goes to 0, delta x over delta t goes to dx dt. Delta y over delta t goes to dy dt, and delta z over delta t goes to dz dt. And that is just one little piece. So to find out the arc length from here to here, I have to sum up all of those delta s's. So that's exactly what I'm going to do next. I'm going to sum up all of those delta s's. And if I sum up all those delta s's, I'm going to sum up my arc length, which was square root of dx dt squared plus dy dt squared plus dz dt squared times dt. And you guys remember from calculus 2, as we let delta t go to 0, this summation becomes an integral. And we're integrating, in this particular case, from a to b. What's the integrand? Square root of dx dt squared plus dy dt squared plus dz dt squared times dt. Time to take notes. If you have a function r of t that is a vectored value function that has an x component, a y component, and a z component, and we want to determine the arc length of this curve from t equals a to t equals b, all we need to do is integrate from a to b the square root of dx dt squared plus dy dt squared plus dz dt squared dt. This you want to copy down. This is an important formula to memorize. You should know it. It can be on your cheat sheet also, but it really should be something that is in your head and you know it. Okay? All right. Moving right along. Let's do an example. Determine the arc length from t equals 0 to t equals 10 of r of t, which equals 3 cosine t, comma 3 sine t, comma 4t. And you all guys know this. This is x, this is your y, and this is your z. So my arc length is going to be the integral, as t ranges from 0 to 10, of the square root of, and first I have to figure out what's dx dt. Well, let's see. Derivative of cosine is minus sine, so this is going to be minus 3 sine t squared plus, then I have to get dy dt. Well, if y is 3 sine t, its derivative is 3 cosine t, quantity squared, plus, what's dz dt squared? Well, let's see. dz is 4t, derivative of 4t is 4, so it would be 4 squared dt. I am using this formula that I just derived. That'd be a cool question on the test to ask you to derive it for like extra credit. That'd be sort of a neat thing to ask. Okay? Now, a lot of times, I'll be honest with you, a lot of times, this, just like when we did parametric, the parametric equations, what was that, chapter 11? When we did that back in Calc 2, a lot of times what's underneath this square root can be a difficult equation to evaluate, a difficult integral to do. In that case, if you can't do it, you can put it on Maple, or you can put it on your calculator and get a numerical value. But I'm going to pick some that are pretty easy to do pencil and paper. This one's an old classic, so let's do this one. So we can go 0 to 10 of square root of, well, this is going to give me 9 sine squared t plus 9 cosine squared t plus 16 dt. And everybody that's in Calculus 3 should know that sine squared plus cosine squared adds up to what? 1. So here, I can go equals integral from 0 to 10. This is square root of. If I factor out that 9, I get sine squared plus cosine squared. Okay, so in this case, sine squared plus cosine squared is 1. So I have a very simple integral, the integral from 0 to 10 of square root of 9 times 1, that's a big old fat 1, plus 16, oh, I picked something so nice, square root of 25 dt. That's going to be the integral from 0 to 10 of 5 dt, which is going to be 5t. And going from 0 to 10, I'll have 5 times 10 is 50, minus 5 times 0 is 0. The arc length is an even 50. Nice, easy little problem to do. Would that be a fair one to put on the test? Absolutely. Because I think everyone that takes Calculus 3 should know sine squared plus cosine squared is 1. Okay? All right, let's do another one. Determine the arc length from t equals 0 to t equals natural log of 2 of, the function is e to the t, comma, square root of 2 times t, and then e to the minus t. Now let's just write out what my x's and my y's and my z's are. X is e to the t, so dx dt is going to be e to the t. Okay, I think you all would agree on that. Y is square root of 2 times t, so dy dt is just going to be what? Square root of 2. And z is e to the minus t, so dz dt is going to be e to the minus t times the derivative of minus t, times the derivative of minus t, which is a minus 1. Okay, now I have to put these into my formula. My formula for arc length, and let's just write it out one time. I think that's helpful. It's going to be the integral from 0 to natural log of 2 of square root of dx dt squared plus dy dt squared plus dz dt squared dt. Notice when you remember from chapter 11, the formula for the arc length with the parametric equation just didn't have that dz dt piece, right? It was dx dt squared plus dy dt squared. Okay, so the more math you have, the more it all comes together. Plugging these in, this gives me the integral from 0 to natural log 2 of square root of e to the t squared plus square root of 2 squared plus minus e to the minus t squared dt. Okay, and let's see, 0 to natural log of 2 of square root of, now e to the t squared is e to the 2t. Square root of 2 squared is 2. The minus squared gives me a plus, but e to the minus t squared is e to the minus 2t. Okay, now you might remember back in chapter 11, you know, Mrs. Strocko is nice and she says use your calculator to evaluate the following. You can plug it into your calculator and get a decimal. Okay, but if I don't, I say evaluate it exactly. All right, well then we got to, what can we do to do this? The only way these work, in order, I mean, there's sometimes, you know, you can make a u substitution or something like that, but usually with these arc-like things, if you've got a square root here, if it can be done with paper and pencil, either you have a cosine sine thing, you know, where you end up with a whole number underneath, or what's underneath that square root might be a perfect square. Okay, and this one actually is. Because notice if I go to factor it, to make the frontsies be e to the 2t, I need an e to the t times an e to the t. To make the backsies multiply to give you e to the minus 2t, I need e to the minus t, e to the minus t. And lo and behold, look what your insies and outsies do. E to the t times e to the minus t is e to the 0, which is 1. Plus 1 gives me 2. So that one factored quite nicely. So what I actually have here is integral from 0 to log 2 of square root of e to the t plus e to the minus t squared dt. And I think most of you would agree, when you take a square root of something squared, you just get what's inside. So I get e to the t plus e to the minus t dt. Now remembering back from your Calc 1 days, the integral of e to the u du is e to the u. So the first one, the antiderivative of e to the t is just e to the t. The second one, let's do a little bit of work. Okay, I want to figure out what's the antiderivative of e to the minus t dt. And let's, some of you are a little bit, you know, some of you it's been a little while since you had Calc 1, Calc 2. Others you know, just forgotten a few little things. Let's review this because it's coming back. I'm going to let my u be minus t. So my du turns out to be minus dt. So I want this integral to be e to the u, but to get that du piece, right now I don't have that minus dt, I just have a dt. So I say, oh, if I put a little minus here and a little minus here, a minus times a minus is a plus. So this minus comes down, and I have minus dt gets replaced with du. So this is equal to minus the integral of e to the u du, which is just minus e to the u. And since u is minus t, we're done. If you can do this in your head, absolutely do it. Okay? I just went over how you would do it with paper and pencil. And notice, to check yourself, the derivative, oh, in fact, we just got this to be minus e to the minus t. The derivative of this should be what's inside. Derivative of e to the t is e to the t. But derivative of minus e to the minus t is going to be e to the minus t times a minus, and it'll counteract that to make it be a plus. Now lastly, why did I pick natural log 2 for my limits of integration? Well, let's plug it in and see what happens. Plugging in natural log 2, this is equal to e to the natural log 2 minus e to the minus natural log 2 minus e to the 0 minus e to the 0. These guys knock each other out. Now, most students would be very happy just to leave their answer like this, But if you look on my little answer sheet, I don't have that. I think I have 3/2. So how do we evaluate that? Well, remembering back from chapter 7, e to the natural log u is equal to u. So e to the natural log 2 is 2. And now this one, there's multiple ways you can do it, but you could write this as e to the log 2 to the minus 1. Minus 1 times a log 2 is a minus log 2. And since e to the log 2 is 2, this is 2 to the minus 1/2. And 2 to the minus 1/2 is 1/2. So this is 2 to the minus 1, which is 1/2. And 2 minus 1/2, last time I looked, is 3/2. Okay? That was pretty neat, if you're a math nerd. Okay, we're doing all right. Let's do another one. All right, now I want to just comment on one thing here. Notice, I think I just lost a paper here, so let me find it. I picked something up and threw it out. Yeah, there it is. Okay, notice, just in review, we have r of t equal to x of t, y of t, z of t. So r prime of t is equal to dx dt, comma dy dt, comma dz dt, right? We just derived, if you wanted to measure the arc length from t equals 0 to t equals t, so maybe here's my curve, here's t equals 0, here's t equals arbitrary t. To represent the arc length on the curve from here to here, it will be this integral. Okay? Now back from Calc 1 or Calc 2, do you remember, we always have to bring stuff back, if you had a function written in terms of an integral, and it just had to be some constant down here, and maybe you had f of t, let's call it f of, it doesn't have to be a t, why don't we make it be f of x dx. All right, do you remember the derivative of this function was just equal, evaluate your integrand at t. You just would pop the t inside. Remember that? Like if you had a function, let's say f of x equal to the integral from 0 to x of sine of 2t dt. If you wanted to evaluate f prime of x, you just would pop the x inside here and get sine of 2x. So, using this, if I wanted to evaluate s prime of t, I would just pop the t in here and I would get square root of dx dt squared plus dy dt squared plus dz dt squared. All right? So that's exactly what I have right here. S prime of t is equal to this. But note, r was equal to x comma y comma z in terms of t, and r prime was equal to dx dt comma dy dt comma dz dt. And remember when you wanted to find the length of a vector, what did you do? You took the square root of the x component squared plus the y component squared plus the z component squared. So this dx dt, a measure of how the arc length is changing as t is changing, is directly equal to the absolute value of r prime of t. Okay, now in the next section, we're going to talk about r being a position vector, and we're going to be talking about v, which is r prime, being a velocity vector. Well, if you think about that, and the magnitude of v, which is equal to the magnitude of r prime, is the speed that the object's moving along the curve. Okay? So think about that. This makes sense. How fast your arc length is changing, how fast your arc length is changing is how fast you're moving along the curve, right? And that directly equals the magnitude of the velocity vector. So it all sort of ties together. But this is one to keep on the side. We have the s dt is equal to the magnitude of r prime. Okay? All right, now, moving along. I want to make a couple comments. I think you probably noticed this when you were doing your homework. The parametric representation for a curve is not unique. Just like the parametric representation for a line, for heaven's sakes. I could have 25 students in my Calc 3 class, and all 25 of you could come up with a different set of equations for a line, right? So and here's an example. I could make r1 of t be t squared, t cubed, and all I did was plug in 2t for t. and I got 2t, 4t squared, and 8t cubed. So I have two different parametric representations for the same line. And what we want to come up with is, in a few minutes, we want to come up with a handle of how can we measure how much a curve curves. How can we come up with some representation at each point along a curve? How much does it curve? We want that number to be large when it curves a lot, and we want it to be 0 when it doesn't curve at all. Okay, so that's what we want to deal with. And we're noticing there's a problem here because the parametric representation for a curve is not unique. It's often useful to use arc length as a parameter. I could fix a point, and I could fix this point right here, and say at that point my arc length is 0. And then I actually could take a tape measure and say, okay, now the person that typed this probably, they don't really look exactly equal, but use your imagination. Let's go an arc length of 1 unit, and let that point correspond to s equals 1. And let's move along the curve another unit, let that point correspond to s equals 2. And go along another unit and let that point correspond to s equals 3. So as you move, so if I wanted to know what corresponds to s equals 10, I just sort of walk along the curve, walk along the pathway, and when my odometer says 10 units, that's the point that corresponds to s equals 10. Arc length arises naturally from the shape of the curve, and it does not depend on the particular coordinate system that you might have picked. Okay? So the question is, if I give you a parametric representation of a curve, could I reparametrize it in terms of arc length? All right, so on this one I'm going to show you how we can do it. Let's reparametrize the helix r of t equals sine of 2ti plus 3tj plus cosine 2t. This should be a k, by the way, people. Typo here, I apologize. All right, with respect to arc length measured from 0, 0, 1 in the direction of increasing t. Now, first of all, before we do anything, I have to know the point 0, 0, 1 corresponds to t equals what? What corresponds to that, to t equals what? What t equals what will give me that point? 0? Sure, 0. If you plug a 0 in here, sine of 0 is 0. 3 times 0 is 0. Cosine of 0 is 1. All right, now, my arc length. Okay, my arc length is going to be the integral from, so this corresponds to t equals 0, the point on the curve. And I'm going to go from 0 to t of square root of dx dt. I'm just using the formula for arc length. Dy dt squared plus dz dt squared dt. Okay, so we're going to do that. We're going to evaluate our arc length. So at the point that corresponds to t equals t, how far is that point from the origin? And let's see, this gives me s is equal to integral from 0 to t of square root of, and let's see, let's move this down so you can see it a little bit better. There you go. What's the derivative of sine 2t? It is cosine of 2t times 2, right? And the derivative of 3t is 3, and the derivative of cosine 2t is minus sine of 2t times 2. We all okay with that? And let's see, this gives me s equals the integral from 0 to t of square root of 4 cosine squared 2t plus 9 plus 4 sine squared 2t dt. And you go, oh, Miss Strocko, I think you can, here's the square root, put together, factor out the 4 out of the cosine squared plus the sine squared, right? This is dt here, dt. I just put the 4 cosine squared and the 4 sine squared together, and cosine squared plus sine squared of any angle is equal to 1. So I have the integral from 0 to t of 4 times 1 plus 9 square root of 13 dt. And so my arc length at the point that corresponds to t equals t is equal to square root of 13t as we evaluate it from t equals 0 to t equals t, which gives me square root of 13t minus square root of 13 times 0, which is 0. So look what we have just done. we have our arc length is equal to square root of 13t. So is it okay if I move that to another sheet of paper? I see people copying, so let me wait a second and I'll take a sip. That's why it's helpful to have people in the studio. Isn't that cool? So what I did was I determined the arc length at an arbitrary point t. So what we have here is s was equal to square root of 13t. So t is s divided by the square root of 13. And so therefore I could write r of s as sine of 2t. For 2t, I'm going to put in 2 times. For t, I'll put in s over root 13. 3, that's a 3, times t, which is s over root 13, comma, cosine of 2t. For t, I'm going to put in s over root 13. And so this gives me sine of 2s over root 13, comma, now 3s over root 3, is it oh, 13, that's good. So it's 3s over root 13, comma, cosine of 2s over root 13. And now we have a parametric representation for the curve in terms of arc length. So it's very doable. No, it's not very doable. I picked one that turns out nice. Sometimes it's not very doable. It can be very tedious. And I tried to pick ones in your homework that turn out pretty nice. Okay? So we can, any curve you give me, I could take that curve and I could pick some point as my fixed point, and I could get a parametric representation for that curve so that if I wanted to know what is r of 3, I would move 3 units along the curve, 1, maybe 2, and I'm just assuming that's what my unit length is, and I would say, oh, that corresponds to s equals 3, whatever the coordinates at that point are. Okay, now why do I want to do this? Well, let's look. Recall, r prime of t is tangent to the curve, right? We did that. R prime of t gave you a vector tangent to your curve. In last night's homework, we defined the unit tangent, right? And the unit tangent was equal to r prime divided by its length, because whenever you took a vector and divided by its length, you got a vector in the same direction, but it was of length 1. Now, I want to look at how much is my curve curving. So it makes sense that I want to look at the unit tangent, because if I make the unit tangent always length 1, how it moves will give me an indication of how much the curve is curving. Okay, now let's look at an example. This is r prime of t, tangent to the curve. Notice t of t would be of length 1. If that's of length 1, it's in the same direction, or it could be in the opposite direction, but it'd be in the same direction, but it'd be of length 1. Okay, now let's look at a couple examples. Here's a straight line. All right, let's draw the unit tangent at various points on this straight line. I'm going to assume this length of my knuckle right here is of length 1. So at this point, a unit tangent would be that long. At this point, a unit tangent would be that long. At this point up here, my unit tangent, use the same finger. What can you tell me about that unit tangent? It doesn't change. If you're on a straight line, you are not curving, and the unit tangent does not change. Now, r prime of t might change because you might be going slower and faster and slower as you're moving up along the curve. You got a little guy walking up the thing, and your r of t showing him walking up the slope. You know, he might be going faster here and going a little bit slower as he gets to the top. Okay, so r prime might be changing length, but r prime's direction does not change. All right, so a straight line, the unit tangent's not changing. Let's look at a circle. A circle, look as I go around the circle. Here's my unit tangents that I drew. You see, they're always changing direction. They're always of length 1, but the direction is changing a lot. Okay, now let's look at a regular curve. I looked at a circle. Circle's like what changes the most. Okay, all right, and let's look at here. Here's just a regular old curve. Now, if you notice, here's a regular curve. Notice right in this section, he's not curving a whole lot, and notice my unit tangent's not moving a whole lot. Here he's curving the most, and you see how the direction of your unit tangent's changing a good bit. And then as you're going straight along here, notice your unit tangent's pretty much going in the same direction. So when the curve is curving a lot, the unit tangent's changing direction a whole lot more. And when you have sections where you're straight, heck, the unit tangent's not changing at all. Okay? So we want to find some way to measure how is the direction of the unit tangent changing. Now notice, if I had, suppose I go along the curve, and here's unit tangent 1. I'll call that Ti initial, and let's let this be T final. Okay, because I'm going from this time to that time. All right, and if I want to compute how much are they changing, you would go Tf minus Ti, right? We would want to compute that. All right, now let me just show you how we can do that. If I take this vector and just slide him parallel to him, but going tail to tail with him, and I make the two vectors tail to tail, this little vector right here is Tf minus Ti, because notice if you take Ti and you add Tf minus Ti, the Ti's cancel and you get Tf. So this little vector right here is representing the difference in those two vectors, Tf minus Ti. Okay. All right, so a change of that somehow would give me, now notice, if I wanted to measure how much Tf minus Ti changes as I change my arc length from here to here, and remember, I could measure Tf in terms of arc length and Ti in terms of arc length, right? And I take the limit as delta S goes to 0, what's that giving me? That's giving me dt ds. But that's a vector. That's a vector. Do I really want to deal with a vector? No, I want to deal with a number to measure curvature. So why don't we take the magnitude of this? Why don't we take the magnitude of this? All right, and for that reason, we are going to define, and this is time to take notes, the curvature of a curve, r of t, is given by k equals dt ds, where t is the unit tangent vector, and s is a parameter that equals arc length measured from some fixed point. Now the problem with this definition is it stinks, and the reason that it stinks is it's measured dt ds. S is arc length. It's the magnitude of the derivative of t with respect to s. So if you don't have your function parametrized in terms of arc length, you have to redo it. And the one I picked turned out quite nicely, but a lot of times it doesn't turn out quite nicely. You with me? And so we say, well, okay, this is an okay way. We're looking at how much is the direction of the arc of the unit tangent changing as I move along the curve. That seems like a nice way to measure my curvature, but how can I get a handle on it? All right, now, don't be copying this stuff down. I just want you to sit back and follow as we go through. All right? First of all, using the chain rule. The chain rule back from Calc 1. The derivative dt dt is equal to dt ds times ds dt. All right, now what I can do is I could divide by ds dt on both sides, and I can get dt ds is equal to dt dt over ds dt. So therefore, the magnitude of this is equal to the magnitude of this over the magnitude of that, or in other words, dt dt is t prime, and ds dt, a few minutes ago we proved that that was r prime of t. Still don't be copying anything down. Okay? All right, so one way to get curvature would be the magnitude of the derivative of the unit tangent vector over the magnitude of r prime to get curvature. Again, this is not the easiest formula to use. Okay? All right. Now, watch this. Again, don't copy it down, but don't fall asleep either. Notice the unit tangent was defined to be r prime over its magnitude, because remember the unit tangent, r prime is tangent to the curve. We wanted a vector that's in the same direction but of length 1, so we divided it by its length to get the unit tangent. So of course, if I took this and multiplied by r prime, magnitude of r prime on both sides, I would get r prime is equal to the magnitude of r prime times t. And at the beginning of the class, we proved that the magnitude of r prime was equal to ds dt. So in this line, I'm replacing magnitude of r prime with ds dt. All right, so I have r prime is equal to this. All right, again, don't be frantically copying. I just want you to enjoy the show for a minute, all right? Now, r double prime, on this side I'm differentiating with respect to time. On this side, I have to use the product rule. The first times the derivative of the second plus the second times the derivative of the first. So the derivative of ds dt is the second derivative times the vector t plus ds dt times the derivative of t, which is t prime. Okay? Right now you're going why, all right? But just to humor me and just follow along. Now, I have this representation for r prime, this representation for r double prime. And just for the hell of it, and some mathematician years ago said, why not? We just came up with this representation for r prime, this representation for r double prime. Let's look at what's r prime crossed with r double prime. Now for r prime, I'm using this representation. And for r double prime, I'm using this representation. We have a distributive property when I listed all the different properties with the cross product the other day. All right, one of them was if you had a vector crossed with the sum of two vectors, it was, you could go this vector cross that vector plus this vector crossed with that vector. So that's exactly what we're going to do right now. We're going to use our properties. Okay, and that gives me, let's fold this a little bit so it doesn't take up so much space. This gives me, okay, let's move this fact over right here so you can see it. I'm going to go this crossed with that. Now, your ds dt and your second derivative of s with respect to time, these are scalars. They're just plain old everyday numbers. So we can factor those numbers out, and we have t cross t. Plus, when I go this times this, the ds dt times the ds dt is ds dt squared, times t cross t prime. But people, remember, when you take a vector and you cross it with itself, you get the zero vector. Just to remember why, remember the magnitude of a vector crossed with itself is the magnitude of the first times the magnitude of the second times of the sine of the angle between them. The sine of the angle is zero. You're getting zero, or the zero vector for t cross t. So in this whole huge piece right here drops out to zero, and we just have this piece. So we have r prime cross r double prime equal to this. So the magnitude of r prime cross r double prime will equal ds dt squared times the magnitude of t cross t prime, which is the magnitude of t times the magnitude of t prime times the sine of the angle between them. And t prime are perpendicular to each other, so their angle between them is 90. Remember, the reason that was the case was because t is a vector that's always of length 1. And remember, we proved last time when you have a vector that's of constant magnitude, its derivative is always perpendicular to it. We talked about moving along around the circle. Okay, so that's sine of 90. Well, sine of 90 is 1, and the magnitude of t is 1. So look what I've got here. R prime cross r double prime is equal to ds dt squared times the magnitude of t prime. Now I know you're sitting there and you're going, why, Mrs. Strocko, why? So let me show you. I want to come up with a formula for curvature. For curvature, I need t prime over r prime. Notice right here, with this equation that I have right here, I can take that equation right there and I can solve for t prime. Let me do it. The magnitude of t prime is equal to r prime cross r double prime over ds dt squared. Now to get curvature, I need the magnitude of t prime over r prime. So to get curvature, I have to divide this side by r prime and this side by r prime. Now, a few minutes ago, a half hour ago, I proved that the magnitude of r prime was ds dt. And so this is equal to, you can either write it as ds dt cubed that way, or you can write it as the magnitude of r prime cross r double prime over the magnitude of r prime cubed. And this is a very, is it an easy formula to use? No. But it's a very usable formula for curvature. So let's go to the chase. This is what I just derived right now. And here's the final formula. Curvature, you usually don't use it this way. You use it this way. One way to represent curvature is the magnitude of r prime cross r double prime over the magnitude of r prime cubed. Do you want to put that on your cheat sheet? Yes. And I think most of you are realizing that some of these, the reason I let you put down these formulas is they get pretty hairy. And that's why you want to have them down. Okay, so you want to save that. Let's do an example using that formula. Okay, find the curvature of r of t, which has components t, t, and 1 plus t squared at t equals 1. All right, so notice, first I'm going to get r prime of t. R prime of t is a vector whose components are derivative of t is 1, derivative of t with respect to t is 1, derivative of 1 plus t squared is 2t. All right, let's do r double prime. That is a vector whose components are derivative of 1 is 0, derivative of 1 is 0, derivative of 2t is 2. Now, since we're asking for, well, let's do it out the long way first. The formula for curvature, let's put it right there, okay? It's r prime cross r double prime over r prime cubed. So first of all, I want to figure out what is r prime cross r double prime. So I have to go I, j, k, then I put down my 1, 1, 2t for r prime, and my 0, 0, 2. I have to figure out what is r prime cross r double prime. And let's see, this equals I times, eliminate the row and column that I is in, and I get 2 minus 0. Minus j times, eliminate the row and column that j is in, and I get 2 minus 0. Plus k times, eliminate the row and column that k is in, and I get 0 minus 0, which is 0. So I have the vector 2i minus 2j. All right, now notice the formula says magnitude of r prime cross r double prime. So the magnitude of r prime cross r double prime is the magnitude of this vector, which is going to be square root of 2 squared, which is 4, plus a negative 2 squared, which is 4. So I get square root of 8. All right, now the bottom of the formula is magnitude of r prime cubed. So coming back here, we have r prime at 1 is the vector 1, 1, and 2 times 1 is 2. So the magnitude of r prime at 1 is square root of 1 squared, which is 1, plus 1 squared, which is 1, plus 2 squared, which is 4, and that looks like it gives me what? Square root of 6. Okay, so I have the magnitude of r prime is square root of 6. The magnitude of r prime cross r double prime is square root of 8. So my formula for curvature was magnitude of r prime cross r double prime over magnitude of r prime cubed. So it gives me square root of 8 over square root of 6 cubed. Okay, now most of you might say, well, that's fine, Mrs. Strocko, I like that, but let's clean it up a little bit. Square root of 8, do most of you realize square root of 6 cubed, you have square root of 6 times square root of 6 times square root of 6, which gives you 6 root 6. We can cancel a pair of 2's here, so because when you both are in the radical, you can cancel. If they're both out of the radical, you cancel. That gives me square root of 4 over 6 square root of 3. Is that right? 2 into the top, 2 into the bottom. Okay, and then if we multiply by root 3 over root 3, because you don't want to have a radical in the denominator, Square root of 4 last time I looked is 2. So I have 2 root 3 over 6 times 3 is 18. And we can reduce that to this. I'm tickled pink on the test if you do that. Quite honestly, if you got to there, I'd be thrilled. Okay? Because there's many things to worry about. Okay? Not hard. So we use this formula right here. I don't use this so much as this. Okay? And I'll be honest with you. 2 days after you take the test, if I asked you what the formula for curvature is, you're going to forget it. But it's a neat thing to see that this, now, in a few minutes, we're going to see why curvature is so cool. But sometimes, right now, this formula is good when your equation is given in terms of parametric forms. What if you just have a two-dimensional graph, y equals f of x, and you want to come up with what the equation of the curvature is, all right? Notice, if you had an equation y equals f of x, it's just, your graph is just in the xy plane. There's no z. Z is equal to 0. All right. So in this case, notice if you wanted to write it in terms of r of t, we could write it as r of x, where your x coordinate was x, your y coordinate is f of x, and your z coordinate is 0. And that's exactly what I did here. R of x, and don't copy this down, just sit back and watch the show for a minute. R of x we could write that way if we wanted to write it as a three-dimensional vector. So of course r prime would be the derivative of x is 1, f prime 0. R double prime would give me this. All right. If I took r prime cross r prime, you would do the cross product. Okay. You can take, if you want to put me on pause, you can double check that what I'm saying is correct. But if I did the cross product of that, I would get this. And if I did this, I would get this. Okay. Don't copy it down right now, just follow. All right. So r prime cross r double prime is equal to f double prime of x times k. So the length of this vector would be however long, however big f double prime of x is. All right. Now, putting this together, since k is the magnitude of r prime cross r double prime over the magnitude of r prime cubed, remember, the magnitude of r prime cross r double prime, the magnitude of this is equal to the magnitude of this, and the magnitude of that is the absolute value of f double prime times the length of k. Length of k is 1. So it's just going to be f double prime. So up top, I just have f double prime. And down bottom, we have magnitude of r prime cubed. Well, here's your r prime. The magnitude of r prime is just going to be the square root of the x component squared plus the y component squared. And I won't write the z component squared plus that's 0. And so that gives me square root of 1 plus f prime squared. And then we cube it because of the 3 there. Okay? So when will we use this formula? We'll use this formula for curvature when your function's given in the form y equals f of x. If it's a two-dimensional graph and you want to measure how much is it curving. All right, so using that formula that I put right there, let's determine the curvature of the curve y equals x squared at x equals 0. And then we're going to save it for a minute and bring it back to show you what on earth does the curvature even tell me. All right, putting this in, let's see what we get here. We have y equals x squared, so y prime is 2x, and y double prime is 2. So my formula for curvature says this is curvature equals the magnitude of f prime evaluated at, we're doing it at 0, well, y double prime is 2, so my numerator is 2, over. And we have square root of 1 plus, now what's f prime? Remember we're doing it at x equals 0. Well, f prime is 2x, and so 2 times 0 is 0. So that would be 0 squared cubed. So my curvature is just 2 over 1 cubed, which is 1, which is 2. So just using that formula, I derived that my curvature at x equals 0 is 2. Now let's save that for a minute because you're thinking, who even cares? What does that even tell me? My curvature is 2. In summary, if your curve is given as r of t, use this formula. And if it's given by y equals f of x, use that formula. Okay, and definitely I would have that on your cheat sheet for the test. But let's tie this together. Why does anybody care? What does this do for me? This is a very important example. Determine the curvature k of a circle whose radius is r. Okay, so I've got some circle, and we'll do it in two-dimensional space. All right, and its radius is r. Well, I'm going to do this parametrically. All right, I don't want to deal with x squared plus y squared equals r squared, because that's not in the form of y equals f of x. You'd have to have two functions to do that. If I wanted to represent a circle of radius r, we could represent x as r cosine t, and we could represent y as r sine t. And since I'm in the xy plane, I'm going to let my z be 0. Okay? So, my vector, my function, r of t is equal to r cosine t, r sine t, comma 0. So r prime is equal to, now remember, r is a constant. It doesn't change. Your radius is r. R could be 2 or 5 or 6 or 12. So if I take the derivative of that, I just get minus r sine t, r cosine t, comma 0. And if I take r double prime, derivative of that is minus r cosine t, derivative of that is minus r sine t, derivative of that is 0. Now, since I've represented my curve parametrically to evaluate the curvature, I'm going to use this formula right here. The r prime cross r double prime over magnitude of r prime cubed. So unfortunately, the first thing I have to do is figure out what is r prime cross r double prime. So I got to go I, j, k. And so I have here minus r sine t, r cosine t, 0. Here I have minus r cosine t, minus r sine t, 0. And let's see. So therefore, r prime cross r double prime is equal to I times, eliminate the row and column that i's in, and God is good. We've got 0 minus 0, so that's good. Minus j times, eliminating the row and column that j is in, I get 0 minus 0 again. That's good. Plus k times minus r sine t times minus r sine t is, in fact, let me put k down here. I need a little bit more space. R squared sine squared t minus, and this is a minus r, which makes it a plus, r squared cosine squared t. Okay, people, help me. I want to save this. Okay. Getting a fresh sheet of paper, we have r prime cross r double prime is equal to 0i, 0j plus k times, what's r squared sine squared t plus r squared cosine squared t? It's r squared, right? Because you could factor out the r squared, and you get sine squared t plus cosine squared t. And this is just a big old fat 1. So r prime cross r double prime is equal to r squared times k. So the magnitude of r prime cross r double prime is equal to the magnitude of r squared, which is r squared, times the magnitude of k. But how long is k? It's a unit vector. It's of length 1. And we have r squared. So we already figured out the numerator for our curvature. Okay, now the denominator is magnitude of r prime cubed. So I say, okay, I can go back there. Notice, here was my r prime, right? So if I wanted to get the magnitude of r prime, the length of any vector is the square root of its x component squared plus its y component squared plus its z component squared, which gives me square root of r squared times, factoring out the r squared. That's a big old fat 1. 1 times r squared is r squared. Square root of r squared, last time I looked, is r. So for the grand finale, my curvature is the magnitude of r prime cross r double prime all over the magnitude of r prime cubed. We got the the magnitude of r prime cross r double prime to be r squared. We got the magnitude of r prime to be r. People, this is why I care about curvature. This is why I care about curvature. So if you've been sleeping, wake up. Curvature is the reciprocal of the radius of the circle. That makes sense. Here's a little tiny circle whose radius is 2. Here's a bigger circle whose radius is 10. I can tell you the curvature of this circle is a half. The curvature of this circle is a tenth. Now you tell me, if I drive around this circle, am I curving as much as when I go around that circle? No. This guy, you got to have your wheels cocked. I mean, it's a sharp turn. So this is a wonderful equation which you should remember. Curvature is equal to the reciprocal of the radius. Now, let's go back for a second and talk about, just to put pieces together, except I don't see the paper I had, so let me a second till I find it. It was the one that we did the curve y equals x squared. And I think I got the curvature to be 2. Let's see if I can find it. Give me oh, here it is, I found it. Back here. Determine the curvature of y equals x squared at x equals 0. Let's go back to geometry for a second before I even look at this. If you have a circle, all right, and I have some point right here, and I drew a tangent line. My tangent line's not too good, but bear with me, all right? I drew a tangent line. What could you do geometrically to be able to find the center of that circle? What kind of angle do you have to make with the tangent line to get there? 90 degrees, right? So if you have the tangent line, to get to that radius, you've got to go perpendicular to the center of perpendicular to the tangent line to get to the center, right? Look at this one. This is cool. We got the curvature. Determine the curvature of the curve y equals x squared at x equals 0, and we got the curvature equal to 2. So if I looked at the curve y equals x squared, and here's x equals 0, and calculus 1 was all about approximating a curve with a straight line. This time I want to approximate my curve with a circle. All right? I want to approximate my curve right at this point with the best circle that I can do. We determined the curvature of that curve at x equals 0 was 2. So the best circle that I could do would have a radius of 1 over k, which is a half. All right? So coming over here, the tangent line's this way. So how would I go to get to the circle? I would go up this way 1/2 of a unit. So if my radius is 1/2, that point's going to be 0, 1/2. Its radius is 1/2, and so I know that the circle whose center is at 0, 1/2 and has a radius of 1/2 is the best circle approximation to the curve at that point. Okay, it's sort of cool. Okay. All right, let's look at something else. Now, remember, before we pull this up, remember yesterday I looked at a curve, at a function, r of t, whose magnitude was a constant number, be it k. We proved, and you can go back and look at the lecture if you want, that r and r prime are perpendicular to each other. We did it with the dot product. We proved that their dot product was equal to 0. So whenever you have a function whose magnitude is a constant, its derivative is always perpendicular to it. So if you have a curve, and we have the unit tangent vector, since the unit tangent vector is always, the unit tangent vector always has magnitude 1, its derivative will always be perpendicular to, its derivative will be perpendicular to it. Okay, t prime will be perpendicular to t. We can prove, but you guys are getting a little bit starry-eyed, so we're not gonna. The derivative always points into the curve. Now, I would love to have a vector perpendicular to my tangent vector that's of length 1. I can have it. I'm going to call him the unit normal. Now, I already know that t prime is perpendicular to t, but the problem with t prime is he might not be of length 1. So to make it of length 1, what do I need to do? Divide him by his length. And this is called the unit normal. It is another vector, and it will be perpendicular to your tangent line. Why does anybody care about the unit normal? He's telling you which way to go. Like if your curvature is a half, go 1/2 unit along that unit normal to find the center of the circle. That's the best approximation of that curve at that point. All right, so here's the definition. The unit normal is defined to be t prime divided by its length, just as t was defined to be r prime divided by its length. So unit normal is you take t, take his derivative, and divide it by its length. The unit normal is always perpendicular to the tangent, and he always points into the curve. And you can see that because if you drew your little tangent vector here, it's always going to be, to take the derivative, you know, it's change in t over change in vector t over change in little t. If you put him right here, you can see that delta t is pointing inside. So he's always pointing inside the curve. Then, mathematicians go a little bit wackier. You have the unit tangent that's of length 1 going tangent to the curve. You have the unit normal that's perpendicular to the tangent pointing into the curve. Notice these two vectors you can determine a plane. And if you wanted to go a little bit wacky, you could talk about the plane that's determined by those two vectors. That's called the oscillating plane. You also could take the plane that's perpendicular to t through that point, and that's called the normal plane. Now, we're not going to go that wacky with it, but if you look in the book, there's problems dealing with that, so I thought I would touch on it. Now, since you have this vector and this vector, why not take their cross product? If you take the cross product, what are you going to produce? Another vector perpendicular to both of them. If I take the cross product of two vectors that are perpendicular to each other, if I take the cross product of t and n, notice its magnitude is length of t times length of n times the sine of the angle between them. Angle between them is 90, so you get 1 times 1 times 1, which is 1. You get a vector of length 1. And it's perpendicular to them. This one, t cross n, would be pointing down into the paper. That's called the binormal vector. The vector that's called t cross n is called the binormal. In this particular case, he's going to be pointing downward into the paper. Okay? All right, one more thing. Determine the oscillating circle of the parabola y equals x squared plus 4 at x equals 0. All right, now first of all, since this is in the form of f of x equals x squared plus 4, and we want to do it at x equals 0, first of all, I want to determine the curvature. All right, in this case, my curvature, I'm going to use this formula right here. So I have to know what f double prime is and what f prime is. So we can do that quite simply. F prime is equal to 2x, and f double prime is equal to 2. Okay, now my formula for curvature is the magnitude of f prime evaluated at x all over the square root of 1 plus f prime at x squared, and then we have to cube that. So this isn't hard. Let's see. F double prime is 2, so the magnitude of 2 is 2. And let's see, f prime evaluated at 0, we picked something very easy as 0, so we have square root of 1 plus 0 squared cubed, and we get a 2. So the curvature at 0 is 2. So if the curvature at 0 is 2, the radius would be 1/2. And so, I don't like that picture. Let me draw one a little bit better. If I drew my parabola, y equals x squared plus 4, it crosses the y-axis at 4. It's crossing the x-axis at plus and minus 2. At x equals 0, I'm right here at the point 0, 4. The tangent line, I picked one easy. My tangent line's a horizontal line there, right, because he's a max. So the unit normals, the unit tangent's like pointing in this direction. The normal's going to be pointing me perpendicular in the y direction. And you just told me my radius would be 1/2. So I'm going to go 1/2 unit down to right here to get to my center. So if I'm going 1/2 unit down, where's my center going to be? At 0, 3.5. So it's going to be the circle whose center is 0, 3.5 with a radius of 1/2, and I can even draw him right there. and that's called my oscillating circle. It's the best approximation to the curve using a circle at that point. Okay, now these formulas, they're hairy. You want to have them, but they're not all that hard. You shouldn't get anything wrong on curvature, you just have to practice a little bit. So between now and next time, first of all, look over pages 898 to 904, and then on pages 904 to 905, I'd like you to do 1, 3, 9, 11, 13, 17, 23, and 29. All right, thanks for bearing with me, and I'll see you next time. Bye-bye.